So we say that a critical point x naught is isolated if there's no other ones nearby. So in other words, there's some small positive distance for which if we look at the ball or disc or what have you of radius epsilon centered at our critical point, this guy contains no other critical points besides x naught itself. Okay, and so now if we're at a isolated critical point and we're looking at a general system like this, so this corresponds to again, x prime is f of xy and y prime is g of xy. Then by Taylor's theorem, so Taylor expansion, we have f of xy is going to be the value of f at this particular point here, plus the partial in the x direction times x minus x naught plus the partial in the y direction times y minus y naught plus some higher order terms. And then we have the whole same thing again for g. Okay, and then since we're at a critical point, the actual value of the function when we evaluate it there is 0. So those ones just drop out. And so what this leaves us with is that if you look at the derivative of, and we take this vector x minus x naught, y minus y naught, so that's the same thing as the derivative of just xy, because the constant vector dies when you take the derivative, right? And so then we've got fx, x naught, y naught, fy, x naught, y naught, and gx, x naught, y naught, and gy, x naught, y naught. So we've got this matrix of first partial derivatives. And there's our eta vector. And so if you consider doing a change of variables where you take u to be x minus x naught, this becomes du dt is f prime evaluated at x naught times u, so you can think of that as the slope times the vector u, times eta of x. I guess that should be a bold-faced eta there. And the critical point now becomes 0 under this change of coordinates.